Okay, so the sky over Washington state was just choked with smoke. You see this mangled mess of twisted steel? That used to be this huge, towering symbol of industry. And this wasn't some slow, sad decline. This was a brutal, instantaneous end. A total catastrophe that nobody saw coming, turning what should have been a normal maintenance day into absolute devastation. So what actually happened here? How does a massive industrial complex built to handle insane pressures just collapse in on itself? This is the story of the Washington Refinery Implosion. It's a disaster where the ground didn't just shake from a blast outward, but from a crush inward, followed by this earth-shattering explosion. Man, I've spent years picking apart industrial failures, digging through all the reports that try to explain the truly unthinkable. And here, that's what everyone missed in the initial shock and awe of this event. A terrifying chain of events driven by not just one, but three killer flaws. Over the next 16 minutes, we're gonna 1. Reconstruct exactly what went down in the moments leading up to the implosion and then that huge explosion. 2. Uncover the specific screw-ups that turned a routine day into total ruin. 3. Reveal the massive consequences that are still being felt today like ripples in a pond. Just a heads up, this whole investigation is based on stuff that's out there in public reports. We've generalized some details to keep things private where it makes sense. The official word on what went down? It all points to a catastrophic failure deep inside a supercritical piece of equipment. We're not talking about a simple leak or a dodgy valve here. It was a heat exchanger, a totally vital part of how they refine stuff that just gave out. But this wasn't some random mechanical oopsie. The Chemical Safety Board's report lays it all out, showing a super complex mix of problems. They found this heat exchanger failed spectacularly, not because of just one single issue, but this deadly cocktail of bad design, operational mistakes, and you guessed it, not good enough safety management systems. This potent recipe led to something that made no sense at first glance. An implosion, followed by an explosion that just wrecked the place. Source: CSB. Seriously, the sheer amount of destruction was mind-blowing. Just picture the immense power it would take to make massive steel structures buckle inward. This wasn't some external shockwave hitting it. It was like an internal vacuum just sucked everything down, a sudden, violent collapse. And then the encore, the explosion. A terrifying crescendo that tore through the entire facility, flinging debris for miles. The scene right after, pure chaos. First responders showed up to this unbelievable wreck, dealing not just with fires but with unstable structures and the constant fear of more collapse. The human toll? Immediate and devastating. Lives were tragically lost. Families were absolutely shattered. And the economic hit in the billions wasn't just felt by the company. It hit the whole region hard. Then there's the environmental mess, this toxic soup of chemicals dumped into the air and ground, a long-term headache that would take years to even figure out, let alone fix. But beyond all that immediate destruction, the big question still hung in the air. How? How could an operation that seemed to be running fine just crash and burn so completely? Accidents this big in industry. They're almost never simple. They're like these incredibly complex tapestries woven from threads of human error, overlooked engineering, and just plain systemic neglect. OSHA's investigations into fatalities and catastrophes usually give you the nitty-gritty details about how these disasters unfolded. You typically see reports about pressure vessels failing, equipment going haywire, or mistakes people made. But this specific kind of implosion-then-explosion event, which is super rare and frankly pretty scary, needed a much closer look. We had to examine not just the nuts and bolts, but the very essence of the refinery's operating procedures and how its materials held up under extreme stress. Source: OSHA. Companies dealing with incidents, this catastrophic, often let slip hints about what was really going on in their public statements. Things like SEC filings, annual reports, 10-Ks, can actually reveal crucial info about their safety spending, the trouble they had with rules, and the massive financial fallout from accidents. These documents, even though they're wrapped up in corporate speak, can shine a light on deep-seated problems that might have been brewing for years, suggesting a culture where maybe cutting costs took priority over safety. Source: SEC Edgar filings. Honestly, the whole regulatory system is kind of a reflection of past tragedies. New rules for preventing chemical accidents, usually announced in the Federal Register, are almost always a reaction. They're born from the wreckage of events just like this one, an attempt to make sure history doesn't repeat itself. Looking at these changes in regulations can show us the specific weak spots that this disaster exploited, giving us a way to understand what went so wrong at the Washington refinery. Source: Federal Register. This whole thing was a harsh wake-up call about the dangers lurking in the petrochemical world. It exposed this terrifying possibility that the very systems built to contain immense power could actually turn against us. The first reports, the stories from people who saw it, the sheer visual evidence, it all pointed to something way more complicated than a simple accident. It pointed to a perfect storm of failures, a convergence of weaknesses all hitting at one single devastating moment. To truly understand this disaster, we've got to break down the specific flaws that led to this implosion and the explosion that followed. These weren't just minor slip-ups. These were fundamental breakdowns, critical weak points that, when they all came together, created an unstoppable chain reaction of destruction. We're about to dive headfirst into the heart of these three deadly flaws, dissecting each one to really grasp how a routine maintenance operation spiraled into one of the biggest industrial disasters we've seen in a long time. The answers are buried in the design, the operation, and the management systems of that Washington refinery. Man, the air in that Washington refinery wasn't just thick with the usual oil and chemical smells. It felt heavy, like something awful was about to go down. And on that day, it did. A disaster, not with a big boom, but a terrifying inward collapse. This wasn't some random fluke. It was the culmination of problems that had been brewing for ages, a nasty mix of design screw-ups and folks not paying enough attention on the job. We're gonna break down the first two major failures that really paved the way for this whole industrial mess. Okay, so, first big problem, a pressure relief valve that was just way too darn small. Think about your pressure cooker at home. You gotta have a way for all that extra steam to escape, right? These refinery tanks were no different. They were dealing with some serious pressure, and the safety rules absolutely demanded good, strong relief valves. But, as it turned out later, there was a critical design flaw. The main relief valve on the tank that was involved. It was simply too small to handle the kind of pressure surge it might actually run into. Design flaw, undersized relief valve. And this wasn't some small detail, folks. This valve was the absolute last-ditch effort to stop pressure from going totally out of control. Its whole job was to quickly balance the pressure inside the tank with the air outside, stopping the whole thing from blowing apart. But its capacity was figured out for normal running conditions, not for those crazy, unexpected situations that can pop up when things go off script. So, when a process started to go sideways, the pressure inside the tank began climbing, way faster than this puny valve could possibly deal with. Honestly, it was like trying to empty out your bathtub with just a tiny little thimble. The pressure just kept building, with nowhere good to go. You can actually put together the evidence of this major failure from a bunch of different places. You've got early inspection reports, which were probably more focused on the day-to-day fixes, and they might have totally missed the subtle implications of a valve's rated capacity compared to how much pressure that tank could potentially build up. Then, you have hypothetical computer models. These simulations, based on how the refinery normally operated and the chemicals involved, clearly show how a pressure spike would completely overwhelm a valve of that particular size. And of course, the big Chemical Safety Board investigation later pointed out how these design shortcomings, including not having good enough pressure relief systems, were a huge reason why this whole catastrophe happened. Source: CSB. This now leads us to our second major screw-up, which is totally tied into that first one, a kind of operational shortcut they took regarding how they handled depressurization. When a process starts to go off the rails, the very first thing you're supposed to do is a controlled depressurization. That means safely letting the stuff inside the tank out to lower the pressure. At this Washington refinery, the maintenance crew ended up having to make a choice during a really critical process upset. Instead of sticking to the book, which was the established, but let's be honest, kind of slow depressurization process, they decided to speed things up. This wasn't some evil plan, mind you, but a risky shortcut, probably born out of pressure to get things back online fast, or maybe they just seriously underestimated the immediate danger. The normal way of doing things likely involved a bunch of careful vents, letting the pressure ease down nice and slow, safely. The way they did it instead, though, probably skipped over some of those really important steps, trying to get a quicker result. And making that choice? Yeah, that created a seriously dangerous situation. By trying to drop the pressure super fast using a procedure that wasn't the standard one, or was at least modified, the crew might have actually made things worse. That undersized relief valve, which was already struggling, was now facing a situation where how quickly the pressure was changing was also a huge factor. You see this a lot in OSHA's summaries of fatal accidents. People not following the established procedures is a common thread. Of course, figuring out the exact sequence that leads to an implosion takes a deep dive. Source: OSHA. Operational shortcut: depressurization protocol ignored modified. The fallout from taking that shortcut was massive. It wasn't just about the pressure itself, it was about the speed of the pressure change. When pressure drops really fast and isn't controlled, it can put all sorts of stress on the tank walls that wouldn't happen if you were venting it slowly and carefully. So, this rushed depressurization, combined with that weak relief valve, was just a recipe for disaster. The pressure kept building up inside the tank, while the pressure outside stayed the same. It was the perfect setup for the tank to just buckle inward, an implosion. Sometimes, when you look at company filings, like those you can find on SEC Edgar, you get little hints about the bigger, systemic problems that can lead to events like this. They don't always spell out the exact operational mistakes, but these reports can sometimes show you patterns in how much is spent on safety, how well they're following the rules, and even the financial pressures that might push people to cut corners. Source: SEC Edgar filings. The story we've pieced together here really points to a critical failure in both the actual design of the safety systems and, crucially, in the human element, making sure people stick to the vital operational procedures. These two failures, working together like a terrible tag team, kicked off the chain reaction that led to the devastating Washington refinery disaster. So, we've talked about two major screw-ups: the initial design blunders and the operational oopsies. But the third killer flaw, the one that really put the nail in the coffin for this refinery, it was this sneaky, quiet foe, material fatigue, all thanks to corrosion that went totally unchecked and structural weaknesses just festering. This wasn't some sudden, dramatic event, mind you. It was a slow, creeping decay. You couldn't even see it, like microscopic cracks starting to form, invisible to the naked eye. And over time, these tiny little fissures, made way worse by maintenance that just wasn't good enough, created this super-critical weak spot smack dab in the middle of the refinery's whole complicated system of pipes and tanks. Now, based on similar disasters, simulated metallurgical tests show us exactly how years and years of being blasted by harsh chemicals and super high temps can totally wreck even the toughest steel. Source: CSB. Think about it like a chain. Each link is solid, right? But if just one link gets a little bit weakened, the whole dang chain is in trouble. That's what happened here. And the inspection reports from way back. Man, they were often so incomplete or just done in a rush, they completely missed this creeping damage. These weren't just little oversights, nope. These were big chances to head off disaster that just got blown. The equipment, even though it seemed like it was working fine, was basically a ticking time bomb, its structural strength just silently getting eaten away. Then the moment of truth hit. The whole chain reaction, this terrifying cascade of events, kicked off. That initial implosion, which was a direct result of those design and operational screw-ups, acted like the trigger. It wasn't just a simple collapse, oh no. It was this violent inward rush of air and pressure. But get this, that implosion didn't just crush the structure. It actually ripped open a really important vessel, instantly blasting this massive cloud of super flammable gases into the air all around. This was the absolute turning point, the moment it went from just an implosion to a full-blown, catastrophic explosion. And those gases that got released, they met an ignition source, maybe a spark from that first implosion, or an electrical issue nearby, and bam. They ignited with unbelievable force. The pressure wave shot outwards, this deafening roar that basically announced the refinery's final seconds. Source: CSB. The scene right after? Pure devastation. Fire just swallowed the whole place whole, turning intricate machinery into goo and twisted scrap metal. The sky filled with smoke and flying debris, a grim, grim reminder of how deadly neglect and material failure can be when they team up. You know, companies involved in these industrial accidents, they often put out details about how much they spend on safety and any compliance problems they've had. Source, SEC Edgar filings. In this particular situation, the financial records probably told a pretty bleak story, basically hinting at the price you pay when you try to cut corners on safety and upkeep. And that price, it turned out, was paid in lives and in the destruction of the facility itself. The Federal Register is full of records showing how safety rules are always changing, and guess what usually sparks those changes? Yep, tragedies just like this one. Source, Federal Register. The whole point of these updates is to stop stuff like this from happening again. But for the folks at the Washington refinery, well, those lessons arrived way, way too late. That material fatigue, that corrosion no one caught, it had already played its deadly part. All right, let's dive into this. It's about that big BP refinery mess, and honestly, it was way more than just some equipment breaking down. It was a serious wake-up call, you know? Turns out, after digging around, they found problems not just with the old machinery, but with the whole darn system that was supposed to keep this kind of disaster from happening in the first place. Source: CSB. It was a heat exchanger that totally blew it, leading to a whole domino effect of bad design choices, mistakes during operation, and a safety management system that just wasn't cutting it anymore. This all ended up in a horrific implosion, which then sadly led to a massive explosion. Source: CSB. This whole ordeal really hammered home just how crucial it is to have super thorough forensic engineering, a really strong safety-first attitude throughout the company, and oversight that just doesn't mess around. It showed us how often, even when you've got safety rules all written down, they just don't actually get put into practice the way they're supposed to. And the fallout from something like this? It goes way, way beyond just the immediate destruction. For the families who lost loved ones, the pain is just. You can't even measure it. For the industry as a whole, it's a really tough pill to swallow, a stark reminder of the price of not paying attention. Now, you'll often see reports about this kind of thing talking about vessels failing under pressure. Source: OSHA. But when you get a rare event like an implosion and an explosion happening together, we really need to look closer at the science behind the materials and how disciplined operations really are. Because of incidents like this, the government folks in charge have taken a look and, in some situations, tweaked the rules for preventing chemical accidents. Totally a direct reaction to these kinds of major screw-ups. Source: Federal Register. And get this, sometimes companies themselves will actually spill the beans about how much they're spending on safety and what compliance issues they're facing, all buried in their financial reports. Source: SEC Edgar filings. It really gives you a peek behind the curtain at the bigger, systemic struggles they're dealing with. We absolutely have to stay on our toes. Real safety in industry? It takes constant hard work, a genuine drive to learn from mistakes, and a deep, deep respect for the smarts and skills that can actually stop terrible things from happening again. We cannot, for the life of us, forget the lessons learned from this refinery implosion.